Right now, a galaxy roughly 2.5 million light years away is falling toward the Milky Way at about 110 kilometers per second. That part is not new. Astronomers have known that number for decades. What is new is the additional motion that has shown up on top of it. When researchers at the University of Hawaii and several collaborating institutions ran the numbers on a stacked catalog of nearly 250,000 radio sources scattered across the sky, using very long baseline interferometry to pin down their positions with extraordinary precision, the residual motion they calculated for our local group, for the entire region of space where the Milky Way, Andromeda, and a swarm of smaller galaxies are gravitationally bound together, was about 3.5 times faster than the standard cosmological model allows. The number that fell out of the math was something like 260 kilometers per second, when the model said to expect 70. That is not a small disagreement. That is the kind of disagreement that makes theoretical physicists stop what they are doing and stare at their screens. This is not a single galaxy behaving strangely. This is the entire neighborhood of galaxies around us behaving strangely. The Milky Way and every galaxy close enough to be pulled along with it through local gravity are moving through the universe at a rate the equations cannot reproduce. And if the equations are right, that means there is mass we cannot see pulling us in a direction we cannot see, and we have not yet found it. If the equations are wrong, the implications are much bigger, because the equations in question are the equations that describe how the universe has expanded and structured itself for the past 13.8 billion years. Getting them wrong would mean our basic picture of how the cosmos is put together has a hole in it the size of a continent we did not know existed. What we are watching right now is not a doomsday scenario. It is not a galaxy about to smash into us tomorrow. It is a slow, persistent, deeply unsettling mismatch between what we expected the universe to look like in our region and what it actually does look like. And the bigger the mismatch gets, the more urgently physicists are asking a question they hoped they would not have to ask this soon. Is the standard model of cosmology still right? Or are we finally catching it doing something it is not supposed to do? To understand how strange this is, you have to understand how the standard model of cosmology actually works, because the violation being measured is measured against that model. The standard model in this context is the lambda cold dark matter model, often shortened to LCDM, the framework that has organized essentially all of modern cosmology for decades. It assumes that the universe is filled with a kind of dark energy, represented by the Greek letter lambda, that drives the expansion of the universe faster and faster over time. It assumes that the universe is filled with cold, dark matter, a form of matter that interacts with light only through gravity, holds galaxies together in their spinning arms, and pulls matter into the filaments and clusters we see in the cosmic web. It uses general relativity, Einstein's century-old theory of gravity, to describe how all this mass and energy interact across space and time. That is the model. It has worked spectacularly well across most of the cosmos. It has predicted the cosmic microwave background, the afterglow of the Big Bang, with extraordinary precision. It has explained how galaxies formed and clumped into clusters and filaments. It has given us a numerical value for the age of the universe that lines up with measurements from multiple independent methods. It is, by any reasonable bar, one of the most successful scientific frameworks humans have ever built. But LCDM has known weak points. One of them is small-scale peculiar velocities. Peculiar velocities are the part of a galaxy's motion that does not come from the overall expansion of the universe. The expansion of the universe stretches space itself, carrying galaxies away from each other everywhere except where local gravity pulls them together. Most galaxies, including ours, are doing both at the same time. They are moving away from distant parts of the cosmos at a rate set by the Hubble flow, which is the global expansion rate. But they are also moving locally, tugged by the gravitational pull of nearby structures. The Hubble flow works like this. A galaxy 100 million light years away is moving away from us at a rate determined by the Hubble constant. A galaxy 1 billion light years away is moving away faster. A galaxy 10 billion light years away is moving away much, much faster. That is the expansion. It is consistent across the sky and gets smoother as you look at larger and larger patches of cosmos. But if you look at a region around the Milky Way, the local cosmic neighborhood spanning maybe a few 100 million light years, you see something different. You see galaxies moving not just with the expansion, but also with their own extra motion, peculiar velocity imposed by nearby mass concentrations. Andromeda is moving toward us because our combined gravity exceeds the expansion's pull in this small region. Other galaxies in our local group are doing smaller versions of the same thing. The Virgo cluster, a massive concentration of galaxies not far from us in cosmic terms, is pulling on its neighbors. The Great Attractor, a region of gravitational pull deep in the direction of the southern sky that astronomers only mapped in the last few decades because it was hidden behind the disk of our own galaxy, has been pulling our local group and the entire Laniakea supercluster that we are part of toward it for billions of years. Laniakea is a structure that contains roughly 100,000 galaxies, including the Milky Way, flowing together toward a common gravitational basin. The word is Hawaiian, and it means immense heaven, which is appropriate. The supercluster is roughly 520 million light years across. We are inside it, we are moving with it. We have been moving with it since before humans existed, since before the sun existed, since before the Earth was even a thought in the cosmos. When astronomers want to describe the motion of our local group through the universe, they normally add up three components. The first is the Hubble flow, the expansion contribution. The second is the gravitational pull of nearby large-scale structures, like the Virgo cluster and the Great Attractor. The third is the dipole pattern of the cosmic microwave background, which is the small systematic difference in temperature across the sky, caused by our motion relative to the rest frame of the universe. From that last measurement, scientists had already concluded that our local group is moving at about 600 to 630 kilometers per second, relative to the cosmic microwave background rest frame. That is the standard number. It has been used for years. So when new studies in 2025 and 2026 went looking for the source of that motion, the expectation was that the cause was the known gravitational mass around us. The Great Attractor should have accounted for a large chunk. So should other structures just beyond it, including the Shapley supercluster, the Vela supercluster, and various other concentrations of mass. But that accounting did not add up. The combination of known attractors and the standard cosmological model was producing a number around 70 kilometers per second for the residual motion of our local group. The actual motion, after stripping out the Hubble flow and the local contribution, was on the order of 260 kilometers per second. That is the gap. It is not a rounding error. It is not a small correction factor that someone could absorb by revising a measurement. It is a nearly fourfold discrepancy between the model and the observation. And that is what has made the recent research from the University of Hawaii team, published in late 2025 and now being scrutinized by the broader community, so uncomfortable. Here is the first reveal. The researchers used a technique called Very Long Baseline Interferometry, usually abbreviated VLBI, which combines radio telescopes scattered across the globe to act as a single planet-sized instrument. With VLBI, it is possible to measure the tiny differences in arrival time of radio signals from distant quasars and use those differences to fix the positions of celestial objects with extraordinary precision. From those precise positions, you can track the motion of the radio sources themselves over time. From the motion of the radio sources, you can work backward and infer the bulk motion of the cosmic region they are embedded in. The team built up a catalog of nearly 250,000 radio sources, mostly active galactic nuclei at cosmological distances, and used the entire catalog to constrain the bulk flow of our local region. Their conclusion was that the local bulk flow, the average rate at which our neighborhood is moving relative to the distant cosmos, is significantly faster than the standard model of cosmology predicts. The simplest explanation is that there is more mass around us than current surveys have detected. There is dark matter, or modified gravity, or something else, pulling harder than we thought. But here's the part that makes it stranger. The Great Attractor idea, which has been the workhorse explanation for our motion for decades, has started to crack. New studies published in 2024 and 2025 have argued that the Great Attractor is not the giant localized mass concentration that older models assumed. Instead, it appears to be a broader, more diffuse flow that extends across a much larger region of the universe than previously thought. The flow extends, in the analyses of some research groups, over a region on the order of 70 megaparsecs, which is roughly 230 million light years across. That is a sphere hundreds of millions of light years wide, and our galaxy is being pulled toward some interior point within it. If that is real, then we are not being pulled toward a single hidden cluster behind the Milky Way's disk. We are being pulled toward something spread out, embedded in the cosmic web, possibly even connected to larger scale structures like the dipole repeller. An underdense region on one side of us that pushes matter away, while large-scale flows pull from the other side. The total mass budget needed to explain our motion under these interpretations is enormous, more than there is in some published estimates. And now the second reveal. The same kind of analysis, when applied to other regions, has started to show the same kind of problem. Other galaxy superclusters, in independent studies using different datasets, have shown what cosmologists call bulk flows, large-scale coherent motions across hundreds of millions of light years, faster than the standard model predicts they should be. The Hubble tension, the long-running disagreement between the rate at which the universe is expanding today, measured directly, and the rate inferred from the early universe, has been a known headache for years. But peculiar velocities are different. They are local. They are tests of how much mass is concentrated where. And on those local tests, the standard model is failing in ways that do not match the cosmological tests done on the largest scales. So what is going on? There are several possibilities. You should know all of them because at this stage, nobody is sure which one is correct. The first possibility is the simplest one. There is more mass around us than current surveys have detected. That mass could be dark matter distributed in structures that have been undercounted. It could be in gas clouds too cool and too sparse to show up in optical surveys. It could be in unseen extensions of known galaxy clusters and filaments. The cosmic scaffolding that astronomers know connects galaxies sometimes stretches for hundreds of millions of light years. If those filaments are more massive than we have modeled, if the Great Attractor is not a single dense region but a vast, extended network, then the motion would be explained without breaking any of the underlying physics. We would just need to find the mass. The problem with this explanation is that even the largest current galaxy surveys, including the DESI catalog and the Sloan Digital Sky Survey, and the latest observations from the European Space Agency's Euclid mission, do not see that mass. Either it is in a form that light cannot show us, or it is organized in ways current observational approaches cannot detect. The second possibility is that gravity itself, on these large scales, works slightly differently than the standard model assumes. This is sometimes called modified gravity, and it has been a research thread for years. Some published models, like the so-called MOAND, Modified Newtonian Dynamics, propose that, on galactic scales and beyond, gravity behaves in a way that does not require dark matter to hold galaxies together. Those models have their own failures, particularly when applied to galaxy clusters in the cosmic microwave background. But some researchers have revived variants of modified gravity to deal specifically with the bulk flow problem. The 2025 results have given new attention to those proposals. The third possibility is the boldest one. The standard cosmological model itself is incomplete. Something about how the universe is evolving, how dark energy behaves over cosmic time, how the Hubble constant actually settles from the Big Bang to today is slightly different from what LCDM has been telling us. This last possibility is the one that writers of science features seem to like, and it is also the one most mainstream cosmologists are treading around carefully in print. Big announcements about a new era of physics do not get made lightly in a field that has spent decades building a model of extraordinary precision, but the data is being taken seriously, and the theoretical circle working on interpretations of the bulk flow problem is busy. Now the third reveal, and this is the part that connects everything together. In June of 2026, the Dark Energy Survey Collaboration released a major data release of new measurements of how the universe has been expanding over cosmic time. The dataset included hundreds of millions of galaxies across a wide stretch of sky, and it confirmed something that earlier DESI results had suggested. The behavior of dark energy, the mysterious force that drives the accelerating expansion of the universe, may not be as simple as the original lambda cold dark matter model assumed. In the standard model, dark energy behaves like a cosmological constant, a fixed energy density that does not change over time. The new DESI data, combined with measurements from the cosmic microwave background, suggests that dark energy may be evolving. It may have been slightly weaker earlier in cosmic history, or it may be changing character in subtle ways, in something more complex than a fixed push. That is not yet confirmed beyond doubt. Other measurements, including the very recent results from the Atacama Cosmology Telescope, have some published analyses that suggest the original cosmological constant could still work. The tension is real, sitting at the edges of what the measurements can currently resolve. But DESI has been steadily adding evidence, season after season, and the picture is leaning toward change. Now, why does this matter to the fast-moving galaxy problem? Because the bulk flow measurement depends on a model of how mass is distributed across the universe. If dark energy is evolving, if the expansion rate is not perfectly smooth across cosmic time, then the way cosmic structures formed and clumped is slightly different from what LCDM has been predicting. The Great Attractor era, the period when our local flow started falling toward the densest region of the nearby cosmic web, might have been shaped by slightly different conditions than our standard model assumes. That could change the expected velocity. It could push the model up toward the observed value. It could not solve the problem, but it could narrow the gap. Or it could be that the gap persists after all corrections. And that is when the loudest parts of the conversation start. The biggest scientific risk is that the explanations are connected. Dark matter clumps differently, galaxies organize differently, peculiar velocities are higher, the Hubble tension is real, dark energy evolves, and something we have been treating as the bedrock of modern cosmology has to be revised. That is not a disaster for science. That is how science works. But it is a major reconstruction, and it will take years of careful measurement to confirm or to rule out. Now connect this back to Andromeda. That is the galaxy most directly approaching us. Andromeda is the closest large spiral to the Milky Way, the largest galaxy in our local group apart from our own. It is around 250,000 light years away, more depending on which published estimate you trust, and it has been falling toward us for billions of years. The textbooks used to say the collision is fated to happen in roughly 4.5 billion years. New work published in Nature, including analyses from a research group based in Finland and collaborators, has revised that probability. The chance that the Milky Way and Andromeda will actually collide and merge within the next 10 billion years is now estimated at somewhere between roughly 65% and about 100%, depending on the model, with several studies now reporting probabilities closer to half. That is, in scientific terms, a much less certain prediction than the older numbers. Why is the probability dropping? The transverse velocity, which is the sideways motion of Andromeda perpendicular to its motion toward us, is harder to measure precisely than the radial velocity. Gaia, the European Space Agency's astrometry mission, has refined the radial velocity, but the transverse component carries large uncertainties. If Andromeda's sideways motion is high enough, the two galaxies could swing past each other instead of plunging into each other, or could take longer to fall together. Different published measurements have placed the transverse velocity anywhere from 17 kilometers per second up to values closer to 100. The most recent Gaia-based measurements suggest the transverse component is relatively small, supporting the idea that the two galaxies are still on a collision course. But the margin of uncertainty is large enough that astrophysicists cannot yet lock in the destiny of our two galaxies with high confidence. What the collision probability has to do with the new bulk flow anomaly is this. Both the local motion of Andromeda and the bulk motion of our region are components of the way galaxies behave, when mass around them is pulling in directions the standard model does not fully account for. If the local cosmic mass budget is wrong, the orbital dynamics of the local group are calculated against the wrong model. The collision probability is just one of several predictions that get touched. The trajectory of the Triangulum galaxy, the third largest in the local group, also gets refined. The dynamics of dwarf galaxies around the Milky Way also get adjusted, including the orbit of the Large Magellanic Cloud and the Small Magellanic Cloud, both of which are gravitationally bound to us, but in orbits that are sensitive to the total mass of the Milky Way. All of these things happen in concert, and it is that concert that makes the new bulk flow anomaly particularly important, because it is not just one weird number from one survey. It is consistent with a growing body of evidence that what we call the local universe is not behaving the way the model says it should. So here is the part where the story starts to scale up, and you can feel the full weight of how strange this all is. Cosmology is one of the few scientific fields where the predictions span the entire history of the universe and where the same equations explain data from neighboring galaxies, distant galaxies, the cosmic microwave background, the rates of star formation across cosmic time, and of course, and the clustering of galaxies into superclusters. When those predictions stop matching observation, something big has to give. Sometimes the answer is, our surveys are missing something. Dust, gas, low surface brightness galaxies, halos of dark matter around clusters, all of which astronomers are still cataloging. Sometimes the answer is, the measurements themselves have systematic errors we have not yet accounted for. And sometimes, occasionally, the answer is, the model needs an upgrade. Right now, in mid-2026, we're standing in the middle of those three possibilities. The data is not yet strong enough to choose one. The new bulk flow anomaly is not strong enough to declare the standard model broken. It is very strong enough to declare the standard model incomplete. And in cosmology, incomplete can be as interesting as broken, because it tells us exactly where the holes are. Now here is the part where the lesson gets personal. You have been hearing for years that the universe is mostly dark energy and dark matter, and that the ordinary matter we can see in stars and planets and galaxies is only a few % of what is out there. That is broadly correct. But the new measurements are pushing us to be more honest about what we actually know about that invisible majority. We cannot see dark matter except through its gravity. We cannot see dark energy except through its effect on the expansion of the universe. We can measure where dark matter is by looking at how galaxies rotate, how light bends around clusters, how cosmic structures formed. We can measure how dark energy behaves by tracking cosmic expansion at different ages. But we cannot yet hold a sample of either in a lab. We cannot yet simulate the conditions where they formed. And this is important because every dark matter map, every cosmic web diagram, every deep field image of galaxies strung along filaments that has appeared in science textbooks for the last 20 years has been drawn according to the model. The filamentary structure that holds galaxies together, the voids between filaments where almost nothing exists, the nodes where filaments cross and dense galaxy clusters form, all of these are being sketched against a backdrop whose basic ingredients are mostly unmeasured. The new measurements suggest the backdrop is slightly different from what the picture on the page has been. The filaments might be heavier, the voids might be deeper, the nodes might be denser, the bulk flow might have to be supported by a more massive structure than current surveys have documented. That is a quieter, less dramatic version of an exciting moment in science. There's no headline that says, the universe is broken. There is no mission to save us from a sudden cosmic catastrophe. There is a careful, public, technical process of measuring, comparing, arguing, refining, and remeasuring played out across working groups and scientific journals and international conferences. What makes the story worth telling is the gravity of the question, not the pace of the answer. And the question is, how much of what we have drawn is real, and how much of it is what we expected to be real? To answer that, several major new surveys and missions are either already collecting data or have just begun. Euclid, the European Space Agency's Dark Universe mission, released its first cosmology-grade data in late 2024 and is on a multi-year mission to image billions of galaxies across a wide stretch of sky. The Nancy Grace Roman Space Telescope is being prepared for launch in the next few years, with instruments designed specifically to map weak lensing across wide fields. The Vera Rubin Observatory, finally coming into operation in the late 2020s, will scan the entire southern sky repeatedly, catching transient events, mapping dark matter through weak lensing, and producing the deepest and widest movies of cosmic structure ever captured. DESI continues to refine its catalog of millions of spectroscopic galaxy redshifts. The next data releases from each of these programs will be the testing ground for whether the bulk flow problem persists, gets worse, or solves itself. If the next round of data resolves the discrepancy in favor of missing mass, then the answer is the simplest. There's more dark matter concentrated around us than we knew. Cosmology stays where it is, with a footnote that one more correction was needed. If the next round of data resolves the discrepancy in favor of modified gravity, then the answer is bigger. We will need a more nuanced understanding of how gravity behaves in different cosmic regimes. That would not necessarily overturn dark matter, but it would change how we describe it. And if the next round of data resolves the discrepancy in favor of evolving dark energy in a slightly different cosmic history, then we're talking about a deeper revision. The story of how the universe grew from the Big Bang to today would need an additional chapter. The dark energy chapter, the one we have barely started writing, would have to grow longer. There's a fourth possibility. The discrepancy persists in the same shape and the next rounds of data do not solve it. That would be the most unsettling of the four outcomes. It would mean that something fundamental in the cosmological model is changing on scales we cannot yet see. It would mean that standing on this pale blue dot, we might not know exactly how the bulk of the universe behaves on scales we cannot see. That would put us exactly where physics has been at several times in the last century, right at the boundary of what we know, looking outward into something that almost matches what was expected and does not quite match. That is where cosmologists are working right now. In 2026, that is the state of the question about why our local region of the universe is moving faster than the model says it should be moving. What does it mean for the rest of us? First, it means that the universe is not done teaching us. Every generation of astronomers has had a version of this moment, where the deep picture of the cosmos got a new layer of detail that required a small or sometimes large adjustment in our understanding. The new bulk flow measurement is one such layer. We will adjust. The adjustments will probably keep us inside the family of dark matter and dark energy models that have worked so well so far. But the adjustments may also push us toward recognizing that even a successful model still has corners that need filling in. Second, it means that the unusual mutt,